Awesome. Thank you so much for the intro. Yeah, and like you said, a lot of the work being done here is really great. It's talking about how we can develop better machine learning models. So I wanted to talk a little bit about how we're actually using these machine learning models sort of at the in our big experiments. So talk about some like recent results that have been derived using machine learning. And also then again, how we actually can use these in sort of edge scenarios very close to our detector when we are trying to acquire our data. So first, let me motivate this whole study. Just a quick reminder. So a lot of the work we're doing at the Large Hadron Collider and high energy particle physics is related to studying the Higgs boson. So I'm sure a lot of you are familiar, but just for those that aren't, I'll do a quick recap. So the standard model describes quarks and leptons, matter as quarks and leptons that interact via force carriers described by bosons, including the Higgs boson here. And you can imagine this is all described by like a Lagrangian, or that describes the way all these fields can interact. This nice visualization of all their interactions is shown here. And you can kind of see that in both of these sort of pictures, the Higgs boson is an extremely central piece of it. So we want to be able to understand it better in order to be able to understand the whole structure of this model. Moreover, we know that there has to be more to it than this. The standard model doesn't explain basic sort of observational facts about our universe. The fact, for example, that there's dark matter, the fact that neutrinos have masses, and this large matter-antimatter asymmetry. And one of the things that the Higgs boson is responsible for, or the Higgs mechanism rather responsible for, is that all these particles have some mass. They acquire some mass. And so this is a fundamental piece of the puzzle that we want to understand better. And so measuring this Higgs boson and its couplings to other particles as well as to itself may give us insight into new physics that may describe some of these missing pieces. So that's really what we're after. And so again, what are some of the sort of basic elements of this theory of the Higgs boson? Well, there's this potential, this Higgs potential in the standard model that has this form. It's a quartic potential. There's this mu squared term, which is related to its mass, and then there's this lambda phi to the 4. So this is related to like essentially how it interacts with itself. And this lambda is known as the Higgs self-coupling. And with these signs of mu squared, so mu squared being negative, lambda being positive, this potential takes on this distinct sombrero shape, right? This shape that you see here, sometimes called wine bottle shape. And it means that the Higgs field prefers a non-zero value. That's like a lower energy configuration. So another way to think about it is that early on, when the universe was hot, the Higgs field could be at this higher energy state at phi equals 0, basically in the center of this little hill. But as the universe cooled down, basically the Higgs rolled down to this lower energy state at a non-zero phi. And because of that, there's now this non-zero Higgs field that sort of permeates throughout the universe. And particles now feel this Higgs field and become massive through their interactions with this non-zero Higgs field vacuum. And so this phenomena, this happened all kind of because of this lambda term, right? Because of this exact shape of this potential. And one of the sort of key goals, or you can call it the holy grail of the LHC program and the future LHC program, is really to measure this lambda parameter, this fundamental parameter of the standard model. Okay, so how do we measure this? So we have to figure out what interactions happen because of this potential. And so in the standard model, the relevant part of the Lagrangian sort of ends up looking something like this. So here you have sort of, again, each of these terms maps to some kind of interaction, at least at tree level, that looks like what you see here. So the green term describes, Higgs and 2 top quark coupling. This red one, this is a part of this lambda, describes the so-called trilinear Higgs coupling. So this is 3 Higgs bosons interacting at a single point. This also implies a quartic Higgs coupling, so there's 4 Higgs bosons interacting at a single point. And then actually another part of this term will be that I'll talk a little bit about, I think, is just that the Higgs boson also interacting with W and Z bosons that carry the electroweak force. And so we want to be able to measure these better. And so but it's useful to have a sort of broader context to, to measure these parameters to say how consistent it is with the standard model, right? So we want to parameterize this space in some way that, includes, let's say, deviations from the standard model. And there's many, many different ways we can parameterize this. And so like, that's a whole thing we can get into, but I'll just describe briefly what we've been using recently. It's the so-called kappa framework, which basically means we focus on sort of inserting an additional multiplicative factor in here, which we always call kappa, basically. And so we talk about these modified couplings kappa with respect to the standard model. So if kappa is equal to 1, you have the standard model point. And so a lot of the results I'll show you are talking about kappas. And so here you have kappa lambda that describes deviations for this, primary, this trilinear Higgs interaction. And then kappa 2v describes deviations related to this 2 vector bosons and 2 Higgs bosons. And I'll actually return to kappa lambda 4 a little later, because I think I'll talk, hopefully I'll have time to talk a little bit about that. Okay, so how do we look for this, or how do we produce this at something like the Large Hadron Collider? So the dominant production mode is through this gluon fusion channel. It gives us the best access to this Higgs self-coupling because basically what we want is we want to measure how often we see the production of 2 Higgs bosons, because that's directly proportional to this kappa lambda factor. And even given that, it's still 1,500 times smaller than single Higgs boson production. So this, it is an extraordinarily rare thing to be able to see, and so this is one reason why we need a ton of data, why we need to collect a ton of data in order to do this. There's also this vector boson fusion mode, which gives us access to this kappa 2v, this other HHVV coupling, which is actually even rarer than this one. But for reasons that you'll see, we'll actually be able to actually access or get some information about this coupling as well. Okay, so how do we do this? We use this giant machine of the Large Hadron Collider. So showing you here, sort of the overhead picture view. It's a 27-kilometer in circumference collider on the border between France and Switzerland. Maybe some of you have been there or worked there or visited there. And you can see the Alps in the background and Lake Geneva and Geneva Airport as well. Just to give you a sense of how big this is, in case you haven't been there, you can easily fit the entire IAIFI Institute in its perimeter. So it is quite big. Okay, this is I do this. I'll admit I do this like a lot of talks, and I go to different places and I do it. And sometimes it's not very impressive, depending on how big the city is. So thank you, Boston, for being very compact of a city and to make this point a little bit more impressive than maybe it always is in like Los Angeles or something. Maybe it's not as impressive. Okay, so what is the Large Hadron Collider? It's a proton-proton collider at 13 tera-electron volts center of mass energy. There's 4 interaction points located along the ring. I work on one of these, the CMS experiment here. At each of these interaction points, we collide protons, not just a single proton actually, but actually bunches of protons, such that any one of these collisions ends up looking something like this, where you have like 10 centimeters of like this luminous region where there's lots of collisions happening, overlapping with one another. And so, trying to dig out the interesting physics that's happening out of this is a big part of the challenge. And just to give you a sense of how rare these things are, a Higgs boson is produced approximately 1 out of every 10 billion collisions, which because of our high collision rate, actually is not so bad. It's 1 out of every 4 minutes. So that's actually pretty good rate. And at the end of the day, because the data sizes are so huge, we can actually only analyze about 1,000 collisions. We can only record and analyze about 1,000 collisions per second. We do this using a real-time filter, real-time decision making algorithm called the trigger, which looks at these events and in real time says, yes, this is interesting enough to save, or no, like throw it away forever. We're never able to recover that. And so that's an exceptionally important piece of this puzzle, which again, I'll talk more about later. And like I said, I work on the CMS experiment. I'm not going to go into all the details of this, but for the purpose of this, you can think of it as like a really large 100 megapixel camera that takes detailed snapshots of what's happening in each collision. And yeah, 100 megapixels is because it has 100 million channels, detector channels that each are recording in, interesting information about each collision. And I'll talk more about actually what it looks like. Okay, so how do we detect di-Higgs production? So for a long time, the BB gamma gamma, even though it has a small rate, so this is when a Higgs boson decays to two bottom quarks on one end, and on the other end it decays to two photons. This was thought to be the golden channel, even though it has an exceptionally small rate. You can see there 0.3%, because you can measure photons really, really well, and so that's kind of like a very clean channel. And then you still get a high branching rate. So the Higgs to BB is the largest branching fraction of Higgs. It decays to two bottom quarks about 60% of the time. So most of the time it decays to that. A very slim percentage of the time it decays to two photons. But this was seen as kind of a good balance between getting a lot of events, but then having them be clean enough that you would be able to measure this really effectively. So of course, because the Higgs decays to Bs most of the time, this 4B channel is the largest fraction, but in many ways it's very challenging. First and foremost is because there's a lot of backgrounds. There's a lot of ways to produce 4 bottom quarks or things that look like bottom quarks at the LHC, and so that can be a big challenge. So to make that a little more concrete, you can see here this is showing an event display of a potential di-Higgs event where there's two Higgs bosons that are produced back to back, and then both decay to two bottom quarks. And so what you can see, what happens is as soon as these bottom quarks are created, they essentially immediately hadronize and create these showers of particles. And then we can measure those particles in terms of their tracks and energy. And this is represented here by the yellow lines are the tracks that are measured by the CMS detector. The green and blue bars here are representing like how much energy we measure in different cells of this calorimeter. And then we cluster all of this into these like orange cones that we call jets. And this is what we're then able to analyze and see, is this consistent with a Higgs boson? And so that's what we're trying to do. We're trying to see if this blob of energy and tracks is consistent with this thing, our signal, our Higgs to BB signal, or if it's consistent maybe with some background, something that just looks like a gluon or some other particle that splits to two Bs. And the problem is that this kind of thing happens about 7 orders of magnitude more often than this kind of thing, right? So the background is enormous. So we really need good algorithms like AI to be able to select this out and really tell us what's going on. So I'm going to take a quick sip of water. Okay, so that's the challenge. And I was showing you here actually what it looks like at high momentum. So when the two Higgs bosons have high momentum. And just to show you, because this is also going to be relevant maybe a little later, at low momentum, what happens is that the two bottom quarks from each of the Higgs decays actually get resolved into separate jets. You basically have this kind of like, diagonal pattern that you see here, where you have all 4 bottom quarks. Basically, each one of them makes a separate jet. And this can be actually harder to tell apart from the background because you have a larger background that can like mimic this. But at high momentum, what happens is that the 2 bottom quarks basically get this so-called boosted into this cone of this jet. So because of that, we can actually try to better identify this whole shower as a Higgs to BB candidate. And that's what we'll try to do with some kind of machine learning algorithm. So the question then becomes, what kind of machine learning algorithm should we use? What is like the best type of algorithm to use for this kind of data? And as you probably know, and we talked actually a lot about already in this workshop, in machine learning, tailoring the algorithms to the structure and symmetries of the data is typically a good idea. You want to actually tailor the algorithm to the kind of data you have. So for CNNs, for images, using CNNs is useful because you have this like approximate translation invariance property. So you don't care about whether a dog or a cat is in the top left corner or the bottom right corner. You can still sort of tag this image as being of a dog or a cat. RNNs were used for a long time with language processing because they could take into account the prior context to a word. Of course, nowadays transformers are kind of taking over everything, but nonetheless, the point kind of stands that the algorithms kind of have some inductive bias related to the kind of data. So what about high energy physics data like jets? So there you have a bunch of properties. So one is our data is often distributed very unevenly in space. We have pockets of very high density and then basically empty regions of the detector, which means that our data is very sparse. It can be variable size, so we don't know how many particles are in a given jet. It can be hundreds of particles. It can be dozens of particles. It can vary quite a bit. There's no necessarily defined order. There's no necessarily meaning to the order of the particles, in the sense that it kind of decays so fast that it's hard to define a good order on them. And there might be interesting relationships, especially pairwise relationships between the particles that we want to take into account. So because of all of this, graphs seem to be a potentially useful representation for this. However, there's one small caveat that I'll mention right now, which is we need to imbue this structure with some kind of graph, right? We need to give it some kind of connections, because at least a priori, there's not necessarily a predefined structure on our physics data. So I'll talk about a different choice that we use, but sometimes we even talk about just using a fully connected graph. This may seem a little bit redundant in some sense, but they're kind of similar to what a transformer does anyway with full attention. So this is one way to construct a graph for a given jet. Okay, so how do we do this? We take a jet, which is essentially a bunch of particles and their full momentum, and then we we basically put them on a graph. So what does this mean? We have node features, which are the particles of the nodes in this graph. So in this case, we have 4 vectors, which could be either specified in different coordinates depending on what's the most useful for the application. We can have edge features, so we can actually add pre-compute additional edge features that might be useful. This turns out to be a pretty can make the training more robust or make the algorithms learn a little faster. So for instance, we can compute something like a delta R, which is a region, which is a distance in the detector between pairs of particles. We can also compute global features of the graph. So in this case, a global feature would be the invariant mass of the jet as a whole, for instance. Okay, and then we want to apply graph neural networks to this. And so maybe first I'll tell you what is the main ingredient. I think it's already been described quite a bit, so probably you're all experts. But the main idea of a graph neural network is this message passing operation. So essentially, we take all the neighbors of a given node I and compute a message based on pairwise, basically taking all the possible pairs, running a neural network on those pairs, and then summing up all those messages to basically create an updated node feature. And so we update our node features by summing over or aggregating somehow. It doesn't have to be a sum. It could be a mean or a min or a max, anything that's permutation invariant operation. And in order to basically get an updated set of node representations for a given graph. So this is the main operation that we use. And we actually heard a little bit earlier about some of the shortcomings of this kind of approach. But okay, what do you do once you have this updated embedding, updated sort of node features for each node in your graph? Well, you can do a bunch of different things. So depending on if your targets are node level. So for instance, let's say you want to look at all the particles in your event and decide which ones came from your hard collision and which ones are not so relevant. Maybe they came from pileup or something. You can do this by basically making all your nodes have targets, binary targets, for example, telling you whether they're pileup or not. So you can identify pileup particles as a node target. You can also do global sort of graph level tasks like jet tagging. So this is where we try to identify a shower of particles as being from a Higgs or some other kind of particle decay. You can also do edge level tasks. So for instance, we will sometimes take our tracker hits and embed them in a graph and then try to figure out which pairs of hits constitute part of a good track, because we want to do tracking with these graph neural networks. Okay, so again, coming back to our original problem of looking for these di-Higgs events, we want to be able to use these graph neural networks to identify Higgs to BB decays. So first, I should tell you a little bit more about them. So the main thing we use is the fact that these B hadrons that these Higgs bosons decay to, they have long lifetimes. So they travel order of millimeters in the detector before they decay. And so what this means is that they travel some distance and then they decay, forming these secondary vertices. So these secondary vertices you can think of as just collections of displaced tracks that are displaced some distance from the primary vertex. That displacement is called a flight distance. And so you have all these displaced tracks, potential secondary vertices. These displaced tracks also potentially have large impact parameters, which can tell you something about the amount of energy that that this particle decayed with. Sometimes there's also leptons in these showers. And then finally, because we expect at least 2 secondary vertices, given one from each of the B decays, you can also look at the relative positions of these secondary vertices. So it's useful to think about pairs of secondary vertices and what are their relationship. Okay, so we can then actually think about creating not just one graph, but actually because we have 2 sort of input collections, we have these particles and these secondary vertices. And so there's these 2 separate inputs with different feature vectors, because we can measure things about the particles like their momentum. Then we might also measure things like their impact parameter. Or if we are interested in like uncertainties, we can also, we often have like uncertainties that we can like approximate from the way we measure the track parameter. So this is a covariance matrix entry, which basically tells you how well you measured the transverse momentum of this particle. At the same time, we also have secondary vertices, which have a different set of features. And so we want to use both of these. So like, how do we basically combine these into a GNN? So GNNs, typically consider homogeneous graphs, but you can actually consider heterogeneous graphs in several different ways. One, way is to, basically just do 2 different GNNs, right? You do 2 different GNNs, one on each collection, and then you kind of combine them. There are also many other schemes that people have looked at and studied in the literature. But I want to just talk about another simple one that we actually use in this study, which we actually embed all of these features into some other latent space via neural network. And then once you've done this, you can basically then treat them as a combined graph. So then you can do all, your message passing across all of these elements. Okay, so what particular GNN do we use? We use this GNN called ParticleNet. If you're familiar with this term of the dynamic graph convolutional neural network, or DGCNN, it's very similar. It uses kind of the same underlying architecture. And basically it uses these dynamic edge convolutions to construct the graph based on some closeness and some abstract latent space. So what does this mean? I'll just walk through this really briefly because I think it's good to think about. After the first, in the first block of this neural network, we actually construct the graph based on how close the particles are in the detector. So we actually take each of the neighborhoods are basically the 16 nearest neighbors. So we use k nearest neighbors based on how close the particles are in the detector. But after the second edge convolution block, you can see that there's this arrow going down from the features over to the left. What this means is that we're actually now doing k nearest neighbors in a much larger latent space. In this case, it's a 64-dimensional latent space, and then constructing neighbors based on that. So what this means is that we're letting sort of the graph itself, the GNN itself, sort of decide which neighbors it thinks are useful, right? In terms of, and then the same thing happens as you go deeper. So after the third one, you're finally using, this 256-dimensional latent space, constructing neighbors, and then using that for your final message passing round. And so what we find with this kind of algorithm is that it can identify these Higgs to BB jets with a very, very good efficiency. So 50% efficiency, so true positive rate, while rejecting 99.9% of the background. So only a 0.01%, 0.1% false positive rate. And the other thing we see, is that it improves on the previous algorithms essentially by a factor of 2 in the false positive rate over some of the previous algorithms that were not based on GNNs, based on like convolutional models and things. So clearly something, they're learning something valuable. Just a quick note, because this was talked about. One of the things that I did want to note is that even after doing this training, we always train on simulation because we need to know the ground truth. And in our real data, we don't know the ground truth. So after training on simulation, then we run our algorithms on the real data. but we have to make sure that our algorithms are actually valid to run on the real data. So we have to make sure that there's not significant mismodeling. So there's a lot of work that goes into actually validating this, and this is just like one slide, and there's a nice talk that summarizes all of these methods that go into it in order to actually test and validate that we're actually, we know what all the features that we're using are modeled well, and the actual discriminant that we're using is modeled well. So I won't go into this, but yeah, there's a lot of things that need to be done to actually use this on real data. Okay, but I did want to mention one other thing, which is a study done by a student at UCSD, Farooq Mukhtar, about how what particle net it's actually learning, because I think that's you might have that question right away by looking at that. Okay, this great performance, but what's actually going on under the hood? With a lot of explainable AI methods, I find that it's much more useful to actually ask explicit questions rather than ask like the very vague, like what is it learning, because it can be a lot. You can then sort of pick it apart in that more specific way. So in this case, the way we tried to make that a little bit more explicit is we tried to ask, is particle net learning kind of traditional jet substructure techniques that we've known about and used for a long time? So for instance, there is, I'm now switching slightly the task it's being used for. In this case, it's being used for top quark versus QCD versus a classification. And so we expect top quark jets to have 3 prongs, basically these 3 subjets that you see here that are like easily identified. And so the question we tried to formulate was, is particle net learning to sort of use these subjets in its classification? So is it learning, for example, to create a graph that connects, particles in these different subjets, or is it doing something else entirely? And so what we can do is use this technique called Layerwise relevance propagation to basically find out, which nodes or edges it considers to be the most relevant for a given prediction. I won't go into the details too much there, but this is what it looks like after the first edge conf block. The thickness or the darkness of each of the lines is proportional to the relevance score, so it tells you which of those it thinks is the most relevant. But I want to focus on the last edge conf block. So this is after it's constructed these high dimensional features, and then it's done k-nearest neighbors in this high dimensional space. Now it's choosing what to connect. And so here you can see that it's not connecting the particles that are closest in this detector, and this is like the real space of the detector. Instead, it's like actually kind of connecting more often particles in these different subjets, in these like different colored subjets. And this is just for one particular quark, top quark example. So it's not saying much because it's only one example that we can look at. But instead, we can actually look at what happens over a large sample of events. And what we find is when we compare it to like an untrained particle net model, there's no difference between top quark and QCD jets. So it doesn't connect more often or not particles in these different subjets. But actually, after you train it, it does learn this significant difference where for top quark jets, 40% of the connections of the relevant connections are between these different subjets. So at least we're like seeing that, okay, it's getting some of the sort of traditional jet substructure, although it's only a small peek behind the curtain and not like a full explanation. Okay, so back to the sort of main topic. So looking at these Higgs events, I'm just going to give you an executive summary of the data analysis that follows sort of the development and training of the GNN. So we apply some selections on our events to look on our data to look for, specifically for these gluon fusion or vector boson fusion events. We identify high PT Higgs candidate jets with this GNN score. I also didn't get a chance to mention that there's also a jet mass score. We also basically apply a very similar technique to learn to estimate a better jet mass, which is very important. Because then we can actually I'll talk about it in a second. Because we can basically train these two to be independent, we can then sort of estimate our background using data. So we can actually create a good data-driven estimate for this. And the main backgrounds are, as we said, so QCD looks like this, as well as the production of 2 top quarks is another main background. Okay, so what does this look like in the end? So this is after sort of all this selection, all this data analysis is done. We've estimated all of our backgrounds that you see in the different colors there. And then our prospective Higgs signal is the one, di-Higgs signal is the one you see in red. So you can see that there is like this, small but noticeable potential excess above the background. And this is the most sensitive region. So it's really tight selection on this GNN discriminant. And we're able to extract a signal strength for this of 3.5 times the standard model. So we see, about 3 times as much, signal as you expect, but you can see that there's pretty large uncertainties there as there's still. But the point is that this is a very already you're starting to see some sensitivity to this kind of signal. And in fact, when we actually compare what this looks like, even relative, I'll show it later, relative to other signals, we're actually able to get an upper limit. So the way that these plots, you should interpret them are, this is a 95% confidence level upper limit on the ratio, basically the signal strength of this signal. And so 1 is the standard model. So we want to basically get this closer and closer to 1 until hopefully we discover the standard model, signal. But basically, the closer you can get this to 1, that means the more sensitive you are. So this dotted line shows us what we expect, which is about 5 times the standard model, and then what we observed, which is 9.9 times the standard model, which is this is kind of descriptive of the excess that we see. But the point is that we're getting to this 5 times the standard model range, even just with this analysis, which is already kind of surprising given what we expected. Okay, and then after combining this with all the other channels, because like I said, the 4B channel is not the only one there. There's also people working on other channels. We can actually get to about 2.5 times the standard model. So we're already getting kind of in that neighborhood of being able to get this. And it'll be exciting to see where we are after we collect more data with run 3. Okay, oh yeah, and then coming back actually to the actual couplings, we can then say, what does this tell us about the couplings? And so here, these plots are very confusing, but they show kind of the standard model expected point is this 1 here again. And then the range that you see between these 2 gray bars is telling you what's the allowed range. So now we're basically narrowing in on the standard model point. So this kappa lambda coupling modifier is now the allowed range is now between 1.2 and 6.5. And then for this kappa 2v, the allowed range is between 0.7 and 1.38. Now, the really interesting thing there is that the point at 0 for this kappa 2v has been excluded by much more than 5 standard deviations now from this data. And so what this means is that okay, granted it comes with a lot of assumptions and everything, but in some sense we've kind of discovered that this interaction is there. Because if that interaction wasn't there, your signal would be enormous, and you would definitely see it. So there is some there's already some really strong, potentially strong statements you can make about this data. Okay, let's see. Then how much time do I have left?
About 10 minutes, including questions.
Okay. Oh, including questions. Oh, okay. So I should
feel free to go a few minutes over.
Okay. I did want to talk really briefly about this perspective for triple Higgs production, even though it's very far in the future. As I mentioned, double Higgs production is already very, very small. Triple Higgs production is even smaller. But the cool thing is there you could potentially say something about this lambda 4. So this quartic coupling that's separate from the trilinear coupling. Although in the standard model, of course, these are essentially these are totally determined by one another. And so you could potentially be sensitive to both if there's any deviations from the standard model. Now this triple Higgs final state is much more complex in the sense that there's many different types of reconstruction you could have. You can have all these different 6 bottom quarks be in these different jets. And it can be much more tricky to basically figure out which of the bottom quarks to put together to reconstruct a Higgs boson. And so the idea here is to use sort of these new transformer architectures, and particularly this symmetry preserving attention network, to optimize this reconstruction efficiency. And in the future, we hope to also potentially generalize this to the mixed, boosted, and resolved case. So even give us basically a way to reconstruct the event holistically. I'm going to skip over this though, and just talk about real quick how we're actually doing fast machine learning also to enable this kind of stuff in the trigger. So what does the data processing look like? So as I mentioned, we have these 40 million collisions per second. These go into our first stage of our trigger, which then immediately has to reduce the rate from 40 megahertz to 750 kilohertz after this upgrade, which means it needs to analyze all these events and basically within microseconds be able to immediately, either discard or save the event. So you need to be able to run, if you want to run any kind of machine learning or sophisticated selection there, it needs to be able to run very, very quickly. So if we want to, for example, program an AI model, how do we do this? Because again, the system runs on FPGAs. So we want to be able to take something that looks like this, simple, but can be complicated from the perspective of an FPGA programmer, machine learning model, and program it directly onto an FPGA. So we can use sort of these like general principles of co-design, where we want to sort of, for example, take our machine learning models and compress them using pruning. We can also use quantization to reduce them from 32-bit floating point numbers to 16-bit or 8-bit numbers or less. And then also we can use parallelization to basically parallelize the over the FPGA. And so we designed this software tool called HLS for ML, which is specifically for scientists or ML engineers or ML experts to translate their ML algorithms into FPGA firmware. And I just want to highlight one application because it's really relevant and developed, in collaboration with actually folks here at MIT. So this is an upgraded. This is a B tagger in the level 1 trigger that can actually be used specifically to help enhance this HH to 4B search. So the upgraded level 1 trigger will actually include track information that we could use to build a neural network. So the input features of this neural network are 10 particles within each jet, which include the particle type, momentum, and vertex information. And you can see it can do a pretty good job of discriminating B jets from non-B jets. And we can actually even, and in terms of the actual impact on the analysis, it can give you a factor of 2 increase in the sensitivity. So in terms of the efficiency. So we can collect twice as many of these events that are very rare without having to throw them away at this trigger level. So it can have a very big impact. And the work was done by students to get this actually to fit on the FPGA was really impressive, and basically required using quantization and compression to get this neural network down to 9 bits. And then in the end, you can do it with a latency of 60 nanoseconds and run it every 5 nanoseconds for a new jet, and using less than 12% of the FPGA resources. Okay, and we're also currently studying how we can do this also with graph neural networks. Okay, so to summarize, GNNs are neural networks that operate on graph structured data and are state of the art for many tasks, including HPV tagging. Improving this can help us probe high PT and measure Higgs couplings. This GNN-based HH search that I mentioned is a major contributor to the latest CMS combination and provides strong constraints on these Higgs couplings. FastML allows us to better reconstruct our data and save potentially overlooked data. And there's a community and NSF Institute, A3D3, that's developing open source tools and techniques like HLS for ML to enable this. So thank you.
Questions for Javier?
So my question was regarding the FPGA thing. So for the backend, are you using like Onyx or like Keras or TVMM? Like because I just Googled up and it's like a Python package. So I'm curious how you're like lowering it all the way to like FPGA.
Great question. Yeah. So we use our own kind of homebrew intermediate representation, but we actually are developing together with Xilinx, AMD Xilinx, this kind of flavor of Onyx called QOnyx. So the main problem with Onyx I think is great. The main problem with Onyx is that it doesn't support arbitrarily quantized neural networks. So if you want to do 4 bits or 6 bits or 13 bits, whatever, it doesn't support that out of the box. And so we basically generalized it slightly to allow for that. And that's one of the formats that we use for. So basically, if you can convert your model to this QOnyx format, then you can it can ingest that format. There are other projects that we work with that use things like MLIR and other kinds of things, and these are really interesting and things we're kind of exploring for how to integrate in the future.
Hi, I have a question. When you use this kind of exclusive clustering to have only 3 jets, well, 3 subjects, my question is, we were trying to have the model try to learn, the important connections. My question is, okay, so you only keep the, you have an exclusive cluster and you keep the 3 hardest subjects because it's a T, it's a top quark. My question is, what's the input to the machine? What's the actual input? So you do this CA algorithm to only keep 3 subjects, but then I would think that the machine only knows about the information, kinematic information of the subjects. But on the next slide, I'm really confused what the machine is actually learning. What are those edges?
Yes. Okay. So I should maybe clarify. So the CA algorithm we use is just to kind of help us visualize what's happening. So we don't actually use that in any way in the actual particle net. This particle net model is trained on all the particles in the jet without any reference to the CA, how we cluster or decluster the jets.
Okay, thank you. And you said for the top quarks, 40% kind of effective. It actually learns the 3 kind of hardest jets.
Yeah.
Are you forcing the top quark to have the W? Are you forcing it to have to go to a die quark? So
yes, good question. Yeah, in this sample, this is using this public top tagging data set. It is in fact always forced to decay hadronically. Yeah, W to 2 quarks.
There we go. Yeah, I'm wondering how the multiple interactions per crossing affects this. Are you able to separate out each event first, or does the GNN handle that?
Yeah, that's a good question. We have other kinds of pilot mitigation that run beforehand. You're sitting next to one of the experts on this in CMS, and so those we basically use those as inputs to the GNN and to the training. So certainly there is some pilot mitigation done before our algorithms are trained and inference is run. It's a good, and I think in the end, I should double check this, but I think we find that because of that, they are quite robust to the pilot. Yeah.
Me or someone? Okay. So besides the fact that it's going to make theorists like me have a heart attack, I mean, how close are you to the point where even the initial stage of jet reconstruction and using these algorithms that, of course, theorists love, but maybe you don't need for these tasks, when it starts to come to the fore, where you say, actually, you're going to use kind of a neural network-based strategy for object identification in the first place, as opposed to doing this baseline unsupervised jet clustering from ideas decades old. When are you going to replace jet clustering?
That's a great question, and I've been wondering myself, because I think that is a balance though. How can we do that in a way that's still IRC safe and everything, and still makes sense, to actually compare to theoretical, calculations. Maybe I think that the challenge, the reason why I really got into this is because of this this problem. Some events can be reconstructed as boosted and resolved, and we always have this challenge of combining all these analyses after. And so I was really interested is can I get at least, so still keeping the jet reconstruction algorithms the same, can I at least get a machine learning algorithm like this transformer-based model, can I at least get a machine learning algorithm to tell me which bin should I put this in? Because sometimes it can be put in both. And we can't have that for the statistical combination. That's not valid. So we need to put it in one bin or the other. Which bin should I put it in to maximize my sensitivity to the thing I'm really interested in? Now you're right. Maybe I'm being too. Maybe I'm not being ambitious enough. Maybe I should say, okay, let's not keep the jet clustering. Let's replace that too. But we haven't gotten there yet.
But if I wanted to get there, I mean, in terms of the FPGA resources availability, is it possible to do in that context?
Yeah, you mean at the trigger level?
I just gave your colleague a heart attack.
Yeah.
Um,
Yeah, we did just invest a lot of resources in figuring out this, how we do jet clustering on FPGAs really fast to do this. But I mean, that algorithm is probably not IRC safe, but let's not get into that.
Any other questions for Javier? Okay, let's thank him one more time.